The title of this video is Maxwell to de Broglie. Why am I choosing this? Well, Maxwell had some very unique information that Einstein used in order to come up with his special relativity, which we got this E equals mc squared. So without that value, de Broglie, who actually came up with this idea of matter waves and essentially started off quantum mechanics, that would never have happened without those things. Now, also, Max Planck came up with Planck's constant, and he came up with that based on some information that Boltzmann did. Now, when did these things go on? Maxwell's equations were at the end of the US Civil War. 1865, Maxwell publishes his equations. And the important thing about Maxwell's equations was that it said that the speed of light was a universal constant. Without this information, Einstein and Lorentz and Voigt would never have come up with that special gamma factor, square root of 1 minus v squared over c squared. So that was really the basis of some of those values and those values for relativity. Now, Planck chose his solution to black-body radiation based on the work that Boltzmann did back in 1868. So a lot of this stuff was in the works way before it was actually brought up as some gigantic discovery. So I want you to understand that building on other people's information is really important in science. You cannot claim that this was all genius by one individual, because that just isn't the case. Sometimes it occurs that it's just the luck of being there and having all this information put together to come up with a result. Let's get started here. Einstein, we've spent a lot of time in the relativity playlist of these videos talking about this particular equation. Notice it's not just E equals mc squared, which is the rest energy. This is the total energy, E equals mc squared, and it's really important to see that it's got this V down here. So it involves the velocity of an object as well. So we're taking that into account. Max Planck used some ideas about distribution of atoms and probabilities, and he used this idea to come up with something that would fit the curve of a black body radiation, and it's got Max Planck's constant, which is really small, times the frequency, and that's going to be the energy. Now, somehow, we have to find some relationship between these two. And that's what we're all about here. Before I do that, I want to somehow take this equation and get momentum. I want to express it in momentum. So I'm going to play some tricks here on the screen, and hopefully you can follow along with me. Okay, first step is I'm going to square the energy. Now, why am I doing this? One method to my madness is I can get this square root out of the denominator. So if I square that, then that's going to be m squared. Let's see, let me clean this up. I'm going to square it so that I can get this square root out of there. And what I'm trying to do is get some MVs together, because that's going to be the momentum. So let's see what I can do with that. What I'm going to do is square both sides, so that's going to be m squared c to the fourth over 1 minus v squared over c squared. I don't have any momentums in the numerator. So how do I do that? I'm going to pull a special trick here. I'll even put it in red to make it look a little bit better. Let's say what I'm going to do is I'm going to add a factor like this, m squared c squared v squared over the same denominator here, 1 minus v squared over c squared. And how am I allowed to do that? How can I add something if it's not already there? Well, I'm going to subtract that same quantity, m squared c squared v squared over 1 minus v squared over c squared. So that's a little trick here. These two together is essentially a zero. So how is that going to help me? Well, here's what I'm going to do. Let me get back to the black here so you can follow along here. What I'm going to do is take m squared c to the fourth. Now what you might notice here is I've got m squared v squared here, which that's going to be momentum. So somehow I'm going to make some sense of that. I'm going to take this first factor, 1 minus v squared over c squared, and I'm going to subtract, and I'll put that in red, I'm going to subtract the m squared c squared v squared over common denominator 1 minus v squared over c squared. And then I'm going to do something here, and I'll put this next one in blue. Boy, I've got lots of colors today. This last one is going to be the plus sign, m squared. Oh, I thought I was going to make blue there. There we go. M squared and I'm going to put the v squared there. And then I'm going to put the c squared. All that over 1 minus v squared over c squared. Now, here's what I want you to notice. If I take the square root of this whole thing, if I take this thing and take the square root of it, this is what I want to do. This is going to get me to where I need to get is, let's look at this factor. This m squared v squared, that looks kind of like momentum squared, over 1 minus v squared over c squared. So that's kind of like the square root squared. So this whole thing is like momentum squared. So let's just think of it that way. In fact, I'm going to go ahead and put momentum squared there. Get back to the setup here. So I'm going to say that this is p squared times c squared. Can you buy that? Take this quantity in here, and we're squaring the momentum, relativistic momentum, which is mv over 1 minus c squared. So how does all this other stuff come along for the ride? I'm trying to get to the end of this so that we can make some sense. Well, if we look at, let's reorganize stuff a little bit, and we'll start doing stuff in black. Let's call this p squared, c squared. I just brought this term down. Then let's look at what kind of mess we have here. That's going to be m squared. These are both over common denominator. C4 minus m squared, c squared, v squared. All of this is over, this is going to be a plus sign here. And all that's over 1 minus v squared over c squared. Well, let's take a look at this. What if I factor out an m squared c to the fourth? What's this factor going to turn into? That's going to turn into, and let me put a circle around it. Let's take this thing. I'm just doing this so I can believe myself that I actually figured this stuff out. So if I come over here and look at what kind of factor this is going to be, and I factor out m squared c4, kind of have to know where you're going for this or you're not going to figure it out. But anyway, in the numerator, if I factor that out, m squared c to the fourth out of the first term, it's just going to leave a 1. Then here's where it gets a little tricky. M squared c to the fourth. Well, I don't have c to the fourth there. So what's going on with that? I don't have c to the fourth. But if I'm factoring out m squared c squared, then since it's c to the fourth, I'm going to put this all over 1 minus v squared over c squared, and that's over 1 minus v squared over c squared. So out of all this, these two factors cancel, and all I have left is p squared, c squared, m squared, c to the fourth. Let's be very careful about this now. We spent a lot of time coming up with this form of Einstein's equation. This is the form without momentum in it, and this is the form with momentum. And mainly what we're concerned about is the momentum part. Now, what happens if the mass is 0, like a photon? If that's true, then this term just falls out and we have E squared equals P squared C squared. Or better look at that in this form. E equals PC. Okay, so we have E equals PC, E equals HF. So those two are equal. So we can put the two together pretty easily. But what does it mean? PC equals HF. Hmm. That's what De Broglie was looking at. And he said, well, if uh, photons act like particles and waves, then what about an electron? Would that also act like a particle and a wave? So that's kind of the question of where we're going with this. So let me see if I can make this a little simpler. Let's look at the fact that if we have a wavelength is equal to the velocity of the wave over the frequency. In this case, the velocity is the speed of light if we're talking about a photon. So, don't we have the speed of light and f? Okay, let me take this equation and put it in this form. I'll take the f and divide both sides by f so that I have P C over F equals H. And then that P is the momentum. Now let's divide both sides by P. So I've got C over F equals H over momentum. And then we see that the wavelength is C over F. So finally, De Broglie's important thing is H over momentum. Now remember, that momentum is not just the photon momentum, but that happens to be the momentum of anything. Anything, as it's relativistic. So I could take the momentum of any object and come up with a matter wave for it. And, I got to thinking about it. What happens if something's at rest? Well, things move around all the time. Let's take the electron. I was looking up, we'll do a little research on the electron, and here's what's true about an electron. An electron moves at like 1.010 to the 6 meters per second. Just a free electron sitting around in a conductor. So it's moving around all the time. So momentum is really a better thing to look at rather than mass. We don't worry so much about mass. In fact, sometimes they say relativistic mass shouldn't even be discussed. We should talk about momentum. And that's where I'm going to uh, end up here. And the thing is, what does all this mean? What can we make sense out of this? All right. De Broglie's equation seems really simple. It's like wavelength equals Planck's constant over momentum. It's going to get really difficult, I'm afraid, or not afraid. In other words, I have this playlist or this document that I'm working on that's called In Search of a Quark. Once we can get to the level of a quark, then we know quite a bit about quantum mechanics. And that's the subject that has always intrigued me. So if you dare, on this playlist, we're going to go through some things that will begin with a wave equation. And I'm going to warn you that the wave equation is really going to show something about probability. So we're going to talk about probability. We're going to talk about the wave equation. We're going to talk about a lot of things that I don't know yet because I have to learn them. So thanks for watching this. Comments are always welcome. And I'll see you in the next video.